Ladies and gentlemen, Mr. Cropper here with Onar. We're going to be discussing some physics. Let's see. I say physics evolved, and you say some other stuff. You said some stuff that was batshit crazy, but the hypothesis I offer is that physics evolved. All right, let's go from there.
Yeah, let's. The idea that physics evolved is very obvious to everyone who just thinks about it for 2 seconds, but there's a lot of controversy surrounding it, because if the universe started with a Big Bang 15 billion years ago, there hasn't been much time for evolution of the laws of physics.
What do you mean? Now wait a minute. Hold on. How do you say it's obvious? Propose to me how it's obvious that it evolved then, because my vision of it is a lot of particles came, some of them were stable, some weren't. The universe is made of the stable particles, just like our ecosystem is made of the stable animals. And animals are just a more quickly evolving form. Matter is a slowly evolving form. Animals are a quickly evolving form.
Yes, and what I'm saying is that is so natural to us, to the degree that we find it self-evident to some degree that this must have happened. And people like Wolfram, he's doing the cellular automata stuff, where he's trying to make the laws of physics evolve from very simple, basic, primitive cellular automaton rules. And that's an example of where people take this for granted and obvious. But if you look at actual physics as we know it started something like 14 or 15 billion years ago, or something like that. And then it didn't really evolve. It just started with a Big Bang, and then it went on.
Well, what if the Big Bang was the evolution, was the... Okay, all right. So the other option is that it's sort of inherent in the structure of things. It didn't evolve.
Yeah, but I'm very sympathetic to the idea of that it's only a viable mathematical structure that will survive.
Only a viable mathematical... Now, if we evolve, if it evolved, could there be neighborhoods where there could be a neighborhood with tigers in it and another neighborhood with really slow, fat ducks, but since they're not in the same neighborhood, the ducks are able to survive, the dodo birds?
That could be.
Could we have dark matter and real matter that just haven't touched?
Something like that. All of that is possible, but I'm very adamant to point out that this is now pure metaphysical speculation. And since we have some people in the comments who keep on complaining about the topics we take up, and I'm not going to mention names, especially not oligarchy slayer, but this is a very advanced topic. It's not this is not going to impact your everyday life, and people who have just interested in living a life on Earth right here and right now, this is not for them. This is a topic that's only of interest to those who are interested in the topic of physics and how to pursue various directions of research, right?
I have to call out one of my viewers who went online and made an anonymous post saying that I'm not an objectivist and wrote a 3-page thing. And one of the things he said was that I don't take anything seriously unless it's a political thing that we can use today. So here we are we're having a conversation that's not applicable to politics today. This is absolutely floating in the most intellectual sense of stuff that really can't really have an effect on you. It's really theory.
I have a throwback at that immediately.
Okay.
You're obviously a rationalistic pragmatist.
Clearly. Very clearly.
You're both rationalistic and pragmatist.
The worst of all.
Yes. So, but okay. So, back to physics. So now I've made that statement that this is metaphysical speculation, and it may have significance sometimes in the future if this becomes real physics. Then it will impact all of us. But until then, ordinary people don't have to think and worry about it. So this is only for those who are interested in the topic of physics, very floating abstractions. From evolution, like if we follow Binswanger, we know that everything that survives across natural selection is capable of surviving. And if it's an unstable process that survives across time, unstable, right? It has a fundament. It's brittle. It's destructible. It can die. Then it must basically become teleological. So whenever there's a fundamental possibility of destruction, teleology is the only long-term survival strategy. Like if you have an indestructible crystal, okay, fine, that can survive. But if it's destructible, only teleology is going to be your salvation. So there are two possibilities here. Either the universe is like a crystal, like an indestructible crystal or near indestructible crystal. So the laws of physics are just very static for all eternity until something breaks it or something like that. Or it's a form of evolved system from an unstable process. It's a system that is fundamentally unstable, and it's going to lead to instabilities unless something keeps it in check. And that requires teleology. So if that's true, if the universe is that kind of unstable process across time, then it needs to have some kind of homeostasis. You know what a homeostat is? Like a thermostat?
I know the word homeostasis, but I think of it as stability.
Yes, but a thermostat is a homeostat. It's a special case of that. So okay. The thermostat says if the temperature becomes too high, it turns off the heat. If it comes too low, it turns on the heat, so it increases. So this will then ensure that the temperature stays within a range.
Homeostasis means the stability of the temperature then?
Yes. So homeostasis doesn't apply just to temperature. It applies to any variable. If you have a system that counteracts changes and tries to keep something static in stasis, then you have a homeostatic system. So you can think of the universe then as a form of thermostat, that it has evolved, that tries to keep the laws of physics in a special domain that's stable for the long term.
I think of it more like tigers and their prey and the whole system changing over time. I mean, I think of atoms decaying, and I think of an earlier period when
a tiger is also a homeostat, right? It tries to remain a tiger. So just because you have homeostasis doesn't mean that this excludes the possibility of evolution.
Right. So there's a background of chaos. I guess that's what's interesting is the background of chaos, because if you propose that there has to be a background of chaos if things are evolving, I have to be able to find a background of chaos, and it looks like the laws of physics are very, very non-chaotic, very non-local. All right.
So, like everywhere where you look in the universe, it looks like it's the same laws of physics. So even though the laws of physics only apply locally, it's as if they are valid globally, or at least as far as we can see.
Well, we find entanglement.
Yeah, but that's like today, bad physicists interpret this as a sign of non-locality. It can be interpreted locally. There are several possible interpretations of that, and I'm not willing to give up locality just to tickle some physicists' bad ideas.
Now, I find the Higgs field that is, if every single bit of matter in the universe is all entangled through...
Yes, There's something going on like that. Yes.
Now that just means the law of identity is written in matter.
It is, but it doesn't like the separation of particles where you change the polarity of one photon and then the other one immediately flips, even though it's like a billion light years away. That's not necessary to explain by non-locality. It can be explained by identity. Obviously, it behaves in a very understandable identity way.
Yeah.
But it doesn't necessarily have to be explained by non-locality. If you want to indulge in it, I can give you a local explanation for that.
Well, can't we just wrap everything in a single dimension, like on a piece of paper where we think we've got 3 dimensions, but it's actually a local event?
That's right. So here's the idea. Think of your space as a piece of paper, and that's easier for us to think about. And on this piece of paper, then one of the photons, one of the particles, has a polarity like this. But when if you change the polarity, it's like going to a sheet that lies on top of it, but it's local. It's only like a tiny, tiny fraction of distance. But you move the whole sheet up at once. It's a local movement up into another sheet. So you used to live on this sheet, and your consciousness and your being now transports just 1 millimeter up so that you now are living in the sheet above it. And in that sheet above it, the polarity of this one has changed, but this one other over here immediately changes also instantly. Not because of communication across the paper, but because you moved from one paper to another.
Right. And
so that this means that we're living in one layer, but there's layers of papers that are local near us, but they're not they're out of phase with our reality. So this gives the notion of a sort of like a phased space where you can change your phase with respect to reality, and then you move into other various positions in phased space. So when you look at something that's almost in phase with us, it looks almost like a cloud of probability. It's like a fuzzy cloud. So then when we look at quantum phenomena that are not entangled, like in this meaning, entangled means in the same sheet of paper, right? Like, no, not just entangled.
No, I think it means in the book. It means all the papers are in a book together.
Yeah, that's true. That's true. But okay. But when you make an observation, now it's no longer a fuzzy cloud. The particle has been observed. It looks real. It looks like Newtonian. It doesn't have any quantum fuzziness to it, right?
It never has quantum fuzziness.
Now listen to me. So when you have the two-slit experiment, you have this, for instance, a photon that goes through one of these things, and it looks like it's interacting with itself and creating this pattern. The way you can think of this is that you are living in the sheet, but the photon is living on all these sheets. It hasn't attached itself to a particular sheet yet. So it's like a fuzzy cloud of where the photon is living like a blob, covering many of the sheets in the book, and that creates this self-interaction. But if you make an observation, if you actually observe now this particle, it's like it collapses. They call it collapse, but it's actually just coming into your sheet, and it's only there. So now there's no cloud. Now there's just this real particle that you have observed, and then the interference patterns go away.
They go away.
Yeah, like when you make an observation, then the interference pattern disappears, and you just see one stripe on the other side of the two-slit experiment.
Well, I'm a little bit displeased with that, because they say something happens in one way, but when you measure it, it happens in another way. But you didn't make a measurement the first time. So I'm very displeased with the epistemology that they use there.
What I'm saying here is I'm giving an explanation which is perfectly in alignment with the principle of locality, but you have to accept that there are copies or versions of our space, that are a little bit out of alignment with us. And I believe that this is precisely how free will works. It's like just like when you make an experiment with the polarity of a particle. In our brain produces this cloud of uncertainty with many possible outcomes in layers of sheets, and free will decides which sheet we're going to live on. Some of the sheets are more difficult to go to because it requires more energy, mental energy, but you can actually influence which future you're going to live in, and that is free will. So you're holding in your mind multiple alternatives, quantum alternatives, and you decide which future you're going to live in.
You say quantum alternatives. That's going to...
Yeah. And this, now, again, this is just woo-woo metaphysical speculation. It doesn't have to be like this. This is just one avenue of research that could lead to something actual real. I make this very clear that in the future, we might understand how consciousness is related to quantum mechanics in precisely this way, where quantum mechanics, the fuzzy cloud of uncertainty that we're talking about, is the same cloud of probability in free will, where we are actually the causal factor for what outcome we're going to get from the experiment, so to speak.
Now, is this the microcosm, macrocosm of ancient belief? But you're proposing that it's legitimately the case? You know, the microcosm, macrocosm. The universe is inside of every human. The universe is a version of man.
Oh, that idea. Oh, yeah. It's like Leibniz. What are they called? The holons? No, these tiny particles.
I don't know specifically Leibniz, but it goes clear back to ancient Greece. They had this idea of the universe, that you are a copy of the universe and vice versa.
Yeah, that's like holographic version of I'm very sympathetic to this because in another video we talked about that the sand of pile doesn't exist, right? It's
right.
Only the individual sand grain that exists. But that's not true for the forest, because the forest is not just the sum of its trees, because each tree has evolved through natural selection and adapted to the forest. So a little copy of the forest is in the tree. So in that sense, the forest exists inside every tree. So that would be like if each sand grain was alive, then the sand pile could exist because each sand grain would evolve so that it has sort of a copy of the sand pile inside of it.
Well, I want to say the forestness exists in every tree, but I find more things inside the forest that the tree needs, like wind, bugs.
Yeah, okay. Yeah, so in that sense, the wind also is part of the organisms. So
it's written in the DNA of the organism.
So it's when I say that the forest is in the tree, we have to be careful to not just make it sound too woo-woo. But you can think of it as a mirror. There's a mirror image of the forest and of the natural world inside every living being.
In fact, that's really very true in the sense that tree has immune responses to the bugs that live in that forest. It has chemical signatures to the bugs that live in that forest to bring them for its flowers, to fight them when it's eating it, and
the architecture of the organism mirrors, like in a mirror house, it mirrors the surroundings. Right. And if you have lots of mirrors that you put together, they mirror each other. So you get this infinite feedback loop between the mirroring elements. So each tree mirrors the other tree, and that's where you get this competition for growing tall, which is like a feedback loop between the trees. So it's not just merely that they mirror each other; they are actually a form of mirror house.
Right.
So now think about this. If you say if the universe is like a sand pile, then the whole universe is not reflected in each sand grain. The whole sand pile is not in the sand grain.
Right.
You have one sand grain and another sand grain. If, however, these atoms, everything in the universe, evolved through natural selection, then there's a possibility that each of these entities in the universe adapted to the universe around it.
Well, couldn't it just be stable versus unstable?
Yes, that's one possibility.
But stable comes in the context of the things around it, and that's that's why we say evolved, because
but there are two versions of that. It's the crystal version, where you click into place, and once you have the structure, it's very stable, but it doesn't change.
Well, and that's we find that with life on Earth, though. I mean, we click into place in the following sense. Life on Earth only has a certain number of options for sustaining itself. It has to get energy. It can either get chemical energy from the vents in the ocean floor, or it can get it from the sun. It can either get it from the sun directly like plants, or it can get it by eating something that ate plants. So
I think that's taking it a little bit too far, because you have to abstract to such a high level in order to find that form of clicking in place. It's true, you're absolutely right, but like a crystal, that's not just merely like you need it's a literal, like here you have one entity and you make a pattern of these entities and it stays like that forever. That's not how life as we know it works.
You say forever, but
forever.
Yeah, but I think life is just a very fast-moving microcosm of this event, and this event is very long. These atoms are stable the way that someone might look at elephants and say, "Well, elephants, stable. There you are." Atoms are going to be around for how long? 1 trillion years or whatever.
Yeah,
but. They're not. They're just evolved stabilities, though.
No, that's a claim, and it's a very natural claim to make. But they don't have to be evolved stabilities.
What's the other option?
Clicked into place like a crystal, and in that sense, they have a one-time evolution. That before this they were chaotic, and then clicked into a stable configuration, and then it's done. No more evolution.
Isn't it still evolving? Stuff's falling into black holes.
Could be, but we don't know if it's still evolving.
Well, black holes are eating things.
But that's not the laws of physics evolving.
Is it not?
No, well, it could be, but then now you're in speculative territory.
Well, that's what the insides of black holes allow us to do, is to say that's different.
There's something very, very suspicious about general relativity, and I say that from someone who got an A in general relativity. So I know general relativity quite well. At least I'm not a PhD level understanding of it, but I know enough about it that there's something very, very wrong with it.
Is it simply a description?
No, I mean, here's what, you remember when we were talking about the sampling theorem, the Nyquist theorem, where if you're sampling outside of a certain frequency range, both upper bound and lower bound, then you're basically just don't getting information from reality. And in the same way, if you're trying to use a theory that has been developed using experimental data in this range, if you're trying to make statements about outside of that range, then you're just guessing. And black holes are outside. That's guesswork.
Okay. I also posit that the rotation of galaxies are outside of the body of evidence that was available to Einstein.
I agreed. And there are other alternatives to this dark matter and dark energy thing, because that is very close to woo-woo, because you can just spray paint the universe with free variables.
Job done, write your PhD, go home.
That's right. So if you have a gazillion free variables to play with, you can do anything. Yeah. So it's bad science to say that let's just spray paint the universe with free variables. Now, problem solved.
Yeah.
It has to have predictive value, and it doesn't. They don't predict anything from it, and they get surprised all the time, which means that they're wrong all the time.
Yeah.
So there, as I said, there are two possibilities for the universe. Either it clicked into place, had a one-time evolutionary event like a Big Bang, and after that it just stays very stable with no evolution, or it actually is constantly unstable and it has to constantly maintain itself. And in that case, that opens up for natural selection even today on the laws of physics.
It has to constantly maintain itself. Well,
just like life.
That's it's the reproductive thing that we can't mirror life that well. Maybe saying physics evolved maybe there's just I want a microcosm of evolution in physics, but maybe it's not there.
It might be, but as I said, it might also be this. It just crystallized and magically this is the right mathematical formula for extreme stability. And I mean, there's some very strange mathematical coincidences with physics that imply that there's something magic in scare quotes about the mathematics of physics.
That there's individuation and identity?
Well, think about it this way. We can describe the laws of physics basically with second-order differential equations and 4 dimensions.
Okay. In 4 dimensions.
4 dimensions, space, like you have space-time. And second-order derivatives, so you in calculus you can make a derivative, and then you can make another derivative. So if you take a trajectory, and you make a derivative of that, you get speed, and you make another derivative of the speed, you get the acceleration, and that's all you need
to describe plus the 4 dimensions.
Yes. So now notice how small that list is. Like, what's the odds out of infinite amount of dimensions that it's so close to 0? 4 is almost 0.
Why do you say infinite amount of dimensions? We don't have evidence for...
No, but like out of the possibility, like if you just take the numbers, the natural numbers, there's an infinite amount of them. And there's just no reason to believe that we should be living on a 4-dimensional. You could equally well be living in a 792 million gazillion dimensional space.
What's the 4th dimension?
In this case, in physics, it's time, right?
Yeah, but I am displeased with viewing that as a separate dimension. I
agree.
I like the idea that things exist and events occur to the things that exist, and we call it time. We conceive of that and we call it time, but it's simply events. Events.
No. The Aristotelian term is exactly the opposite of events. It's actions.
Actions occur?
Yes, things act.
Things act.
So when you act, things happen.
Well, I know, but then you have to start with the prime mover to get the ball rolling.
No, okay, but like if you're saying it's events, then you take away like free will because we act.
Well, no. Then I bring up evolution as a tiny microcosmic detail inside of the roiling mass.
Okay. This is like a detail, like we can get lost into this for hours.
Yeah.
But my point is this, like whether you view time or not, like I'm just following kosher physics here with 4-dimensional space. And whether you call time space or not, that's a dimension or not, I agree that it is tricky and I don't like it at all. But for our purposes, why isn't the universe 792 gazillion dimensional? Why it's so close to 0? 4 is a very specific number. And the same is true with differential equations. If it is a differential equation, why isn't it a 797 trillion differential
All right.
equation.
So what are the first three dimensions? Because that's gonna now you're not even gonna get to four. You've got 1 plus time, as far as I can see. What's the first three dimensions? There's
No, you have space. You have three.
See, there's space. That's one dimension. There's events
Well,
in space.
space has structure, so we call those three spatial dimensions, and then you have time. So, but you can split it up like that, space and time, absolutely.
So if I eliminate time as a dimension and just call that events in space, then all we have is our one. Then,
yeah, but in physics, you don't do that. A dimension is a free variable. It's like a variable that you need to describe reality with, and you need three variables to describe three-dimensional space.
Well, I'm not finding the human necessity of describing it a certain way to be written in reality itself. There's one dimension called reality, and then there are things called events over time. Mathematics is...
Sure, but then you're not dealing with physics, right? Physics, we have to follow certain
all right,
rules.
But then don't take your physics system and then say, why is reality like this? You're just describing reality with your physics system.
Yes. What I'm saying is that if it's such a ridiculously low number out of the infinite possibilities, like
one.
if you,
Okay, you proposed three. All right, so I don't find that it's I don't find that it's three. I find that mathematics uses three to understand and explain it. I only find reality.
Why isn't space four-dimensional, five-dimensional, or six-dimensional?
It's not three-dimensional. It's only one-dimensional. It's just particles having events over time.
No. That's like saying that everything is God.
If the Higgs boson is true, and if the law of identity and the Higgs field is true, then it is one-dimensional. There.
No.
QED.
In the standard model, you have 12 independent variables that you need to identify experimentally. So you're not getting to use quantum mechanics and quantum field theory for that.
Well, isn't it the case that every single item in the universe is entangled through the Higgs boson?
But now you're sort of moving down. Like we can sort of float up there and say that everything is God, everything is connected. But then we're sounding like some kind of guru, like meditator, kind of mystic. When
you say there are these three categories and then there's this fourth, and why these numbers, that's a lot like it's a lot like Newton saying, why are there 7 planets? And he just couldn't get his head around why 7 planets.
No, but I don't care about whether it's 3 or 4 or 5. I'm caring about why is it only 3 and not 395 billion.
But why is it only? So I would have to ask the question: why can I only find one, which is the Higgs boson, the Higgs field that unites all particles entangled?
That's because you're waving your hands with woo.
I like the Higgs field. I think it's just the law of identity. I think we've just found the law of identity. Scientists.
But even so, I'm very skeptical of modern physics. There's so much strange stuff going on there that we don't understand. And we're lots of hand waving. And I can guarantee you that one thing I'm sure of: the Higgs boson, their Higgs particle, is not the final answer. There's so much thing that's totally wrong.
Do you know what upsets me about it is that if the modern system has evolved in some sense, if there were previous eras in which there were things and today's system has arisen from those, if that were the case, then smashing those things apart in a high-speed machine isn't necessarily going to move us back. It's only going to move us back if things clicked into place, as you say.
Yep.
So if things did click into place, I guess we are learning by using that machine.
Yeah, and that's the assumption that's built into the universe, that or into physics, I mean, that the laws of physics haven't evolved.
Right. So where do you finally stand on that?
I'm very open both ways. I have like the suspension of belief.
Waiting for evidence?
Yes, it's like I'm willing to say that I'm temporarily not believing in what we know, just to, while I'm in that suspended mode, trying to be creative and find alternative. I'm perfectly aware of what I'm doing, and when I'm finished with it, I remove the brackets, and then I'm back into my knowledge space. But when I do that, I said, I'm not going to limit myself to say, I have to believe that this is true versus this is true. I'm going to let them float out there and fight it out. Right. So I'm not saying that the crystalline version of reality is false, but I'm also not excluding natural selection. So I'm constantly weighing alternatives against each other. But
can there be a mixture? Can it be a mixture?
Yeah, of course it can be. So, for instance, as I mentioned in another video, I think, like you have the so-called division algebras. How many? If you start with the real numbers, that's very like a basic number system, and you can do adding, subtraction, multiplication, and division with them. And then you ask yourself, if we now add more dimensions to this, how many number systems built over the real numbers can have these adding and multiplication rules? And it turns out that there are only 4. And they are the real numbers, the quaternion, the complex numbers, the quaternions, and the octonions. And they are 1, 2, 4, and 8 dimensional.
No 16.
No 16. It
Why?
Stops it. Because in every step you lose a mathematical property. So you start out with real numbers that has its commutative, it's associative, but when you go, and the same is true for the complex number, but when you go up to the quaternions, you can't switch order, then it changes the outcome. So it loses commutativity. Okay. And when you move up to the octonians, it loses associativity. If you have A times B times C, then you have 2 possibilities. You could have A bracket B times C, and you have A B bracket times C, and those are no longer equal to each other, so you lose associativity, and you only then remain a limited form of associativity called alternativity. So when 2 of them are equal to each other, it works. So A times C, you can have associativity with. But at 16 dimensions, you lose alternativity, and from there onwards, it breaks down.
Okay, interesting as far as those aren't floating abstractions, which a lot of them are for me, but...
Now, the real numbers are abstracted from reality because we use them every day, and complex numbers are used all the time with anything that has to do with waves. Wave phenomena has to do with things that, like, you can make it go around in circles. And as a matter of fact, quantum mechanics requires these complex numbers. So if you look at the basic differential equation describing quantum mechanics, it has complex numbers in it. And if you go up to the quaternions, when Maxwell formulated his theory of electromagnetism back in the heyday, in the 19th century, he actually used quaternions to do that, because quaternions give you a strange thing called a cross product, which has a very strange quality, and he used that cross product to formulate I don't know if you have done in electromagnetism where you have the right hand rule. You're pointing the fingers in all sorts of directions to find. Okay, if you're not familiar with that, like if you go into a physics class, a beginner's physics class, people stand like this and trying to find out which direction the electricity is flowing in, and so forth. So he used basically quaternions to describe electromagnetism. So now, later they said, oh, this quaternion, we don't need the whole thing. We're just throwing out the quaternion, and we're just keeping the cross product. And what happened is then basically that the laws of physics needed 3 out of these 4 division algebras. And these division algebras are special because they are called exceptional, because in physics or in mathematics, you can just generalize things. You can just make infinite stuff about things. You just generalize. But here's something that stops. You can't continue generalizing. It stops after 4.
Okay.
And then I noticed that the quaternions has like one real number and 3 imaginary numbers. So it has a 1 plus 3 structure. And the 3 imaginary numbers can be used to do operations in space. So it's like, doesn't that look a lot like space-time? And a lot of people have noticed this, but it's very hard to get something out of that. Because in the end, the physicists say, no, we don't like that, we're throwing it out, we're just going our own way. Physics going their own way. Piggy-tow.
Nice. Nice.
Yeah. So what I'm saying is that, maybe it's not a coincidence that we're living in exactly the kind of space we're living in, and it's a special kind of physics that we can get from the division algebras. So what's so special about the division algebras? Well, they are conservative. So if you take an 8, like a 4, okay, let's stay with complex numbers, 2-dimensional. In a 2-dimensional, you have an x and a y coordinate, right? And then now you can use Pythagoras to find the length of this vector, right? So the length is going to be the square root of x squared plus y squared. That's Pythagoras. That's the length of this thing. Now, what you have is that when you take any complex number, you can describe it with an x and a y coordinate. So that it has a certain length, and if you multiply it with another complex number, you can multiply them together. Then you find out that when you those two multiply together, has the same length as the length of one multiplied by the length of the other.
Okay.
So if one has length 2, the other has length 4, when you multiply them together, they have length 8.
Right.
So they conserve the norm, the length of the vector. It has a conservative property.
Okay.
Now, and when I say conservative to you, what do you think?
It's embedded inside of or is entailed in the new result.
And therefore, it's somehow surviving.
Yeah, okay.
So it's a viable structure for going on and going on.
Okay, fair enough. Yeah.
So what I'm saying is that, these conservative numbers, the division algebras, I have a strong, strong feeling that they are chosen by natural selection for physics precisely because they are conservative. And conservative in the physical sense that they conserve properties across time.
Uh-huh. Okay. And now, can we ask why that happens, or is that just is that just a fact?
For now, I have to just say that for some weirdo reason, this is just a fact. These are not arbitrary rules. If you start out with the real numbers, this is the way to do it. There's no other way. These are the only division algebras that are possible to make.
Interesting. All right. Well, this is fun physics, math physics. What are we doing here? Metaphysical math physics?
Mathophysics.
Mathophysics.
Or crystal math.
Whoa. Well, that'll be the title of this video.
Crystal math.
Oh yeah. No, we didn't say enough about crystal math.
Not crystal meth, no. But it's like it does have a crystalline structure to it. And what does it mean that when you have one dimension and you conserve multiplication, you sort of understand what that means. 2 times 3 equals 6. Okay, fine, I understand that. But what if the length was 1? 1 times 1 equals 1. Now you have this is called the identity element.
You can't get anywhere with that, though.
But you have the law of identity.
Yeah. Oh, okay.
1 times 1 equals 1.
Which is why we exclude 1 as a prime number, because it doesn't get you anywhere if 1 is a prime
number. Because it's the identity.
Yeah. You've got to talk about relationships between things to get anywhere at all. You can't just reiterate the thing.
And notice here now, this is very interesting, because mathematics, this is conservative, and you have a law of identity. This sounds very philosophical, right?
Yeah. Well,
and it sounds like it's very suitable for A remains A. 1 times 1 remains 1. So what do you get when you just have the number 1? That's boring. 1 times 1 equals 1. But if you have 2 dimensions, complex numbers, then it's not the numbers it's the length that remains 1. So what you do is that when you multiply this vector, the complex number, with this complex number, and both have length 1, they lie on a circle, and then you just rotate on the circle. So it's anything that has on the circle has length 1. The radius is 1, right? And this means that if you multiply some complex number that has norm or length 1 with another complex number that has length 1, it will remain somewhere on the circle, but you can get circular motion.
I don't know. That's a mathematical thing you're saying. So I'm not following.
Okay, just very simply, if you have a circle, the definition of a circle is it has constant radius everywhere.
Okay, fair enough.
And the unit circle, identity circle, is called the unit circle, or the identity circle, has radius equals 1.
Okay, right.
So you have a unit circle, and if you now take any complex number that lies on the unit circle, any complex number, and you multiply it with another number that lies also on the unit circle, the result is going to be somewhere on the unit circle. So it stays on the circle. That's just a fact of mathematics. It's very cool, and this is called in math theory. This is called a group, because you stay inside the group. So the circle, unit circle, is a group, and the actions conserve your position inside the group. But you can be anywhere in the group. So this is now describes rotation on a circle. And the point of this is only the only takeaway you have to take from this is that circles are conservative. Whenever you have wave phenomena, you're dealing with something that conserves itself across time. Well, the wave propagates, right? It reproduces itself.
That's true.
So you can understand that a wave that goes across the ocean can be thought of sort of like a wheel rolling around. So if you look at the wave, and then you're trying to follow it, and you can have a wheel turning along with it.
Yeah, bicycles make that. The bicycle blinkers make those.
Yes, right. So you have a circular motion of up and down. So this up and down motion is the same you get of a circle going in circles.
Is that the math? Is that the mathematical? Is that the instantiation of any given instance of the math that's going on? Is which bit of the wave is?
Yes.
Now, what do we? Okay, what do we? So what do we do with that? So waves are a
circle. Yeah.
A circle.
Yeah.
It gives identity. Motion. It gives an individuation identity to waves.
Yes. Now, so the point is that what do we have in quantum mechanics? Waves,
which have individuation identity at their core necessarily.
Yeah. And the waves they get from this complex number. So they're using the complex numbers. And those complex numbers are the ones that create the wave phenomena. So when we say that light has a wavelength, that we're making use of these complex numbers.
So somewhere buried inside there is a 1.
And square root of -1.
And the square root of -1.
Yeah.
Well, that was a jump. Where did you? Okay, the square root of -1 is
That's what they call when you have the complex numbers. You need to have also the square root of -1 as a form of identity.
Oh, okay.
So think of it like this: if you have square root of -1 and you square the square root of -1, what do you get?
-1, presumably.
Yes. So you get here. Now, what do you get now if you multiply -1 with the square root of -1? Minus the square root of -1. That's here. And what do you get if you take minus the square root of 1 multiplied by the square root of minus the square root of -1 multiplied by the square root of -1? You get -1 times -1 equals 1. So if you multiply, it goes in a circle. So now, of course, I am not expecting you to understand it from that simple. I should have written it down like and simple. But basically, when you multiply by the square root of -1, just keep on going in circles. Uh-huh. Just you iterate it, doing that.
Which seems like identity.
Yes, you're staying on the circle.
It seems like the individual. It seems like saying that there is a 1 somewhere.
Yeah. Now notice that this is. It's very difficult to go from this to say that now I understand the universe. It's all is one, because that is what's it? This guy called Deepak Chopra, or yeah, he does that. He says some fancy things that sounds scientific and using mathematics, and then he says, from this we know that all the universe is one. So that leap sounds good, but it's actually just waving your hands. First you say something that is correct and true, but then you make a leap that is too much. So we cannot, from what I just say, oh, everything is one, or something like that. Because we have to build it up step by step and show it all the way. Otherwise, we're just making a floating abstraction. Mm. But the point is, we can sort of hint at seeing that, I can see that there's something here, right? You're seeing that this seems to be important, but we don't know the details yet. But it warrants a lot of research. So what I'm saying is that I'm very interested in the 8-dimensional version, the octonions, because it too has this very strange conservative property that 1 times 1 equals 1. That you can rotate around in a circle, but not a circle, but an 8-dimensional sphere. Hmm. Now that's crazy, and but it's not more crazy than when I think about the kind of structure it has in common with what we observe in reality. It's very close. It's very, very close.
An 8-dimensional sphere?
Yeah.
How is reality?
Now let's first take the 4-dimensional sphere case. Okay, we have space and time. We have 3 dimensions.
Yeah.
If you're standing on a 2-dimensional sphere, like our Earth, 2-dimensional sphere, then well, we call it. Let me not use
the surface of the Earth is a 2-dimensional space.
Yes. So that's why they call it a 2-sphere. But for non-mathematicians, let's call it a 3-dimensional sphere, because it's embedded in 3 dimensions. Our globe, our Earth, is 3-dimensional, but you have 2 directions you can go in: north-south or east-west, right? So those are 2 fundamentally. It's like you can have an X and a Y coordinate system that describes your motion. Okay? If you are on the 4-dimensional sphere, you can move in 3 dimensions, X, Y, and Z.
Can we? Is there a parallel to the fact that at the North Pole you can only move south, and at the South Pole you can only move north?
Now here's a strange thing. this is really freaky. Our globe, the three-dimensional globe, has a pole, a north and a south pole, so that when you rotate it, the point stands still at that north and south pole. The four-dimensional sphere has no pole.
Okay, so there's no parallel at all to...
No, but this is very strange, and it's very unique. Most spheres have poles, but there are only three spheres that have no poles. And that is the circle. Then it's rotating around the center. There's no pole when you rotate the circle. It's rotating around the origin, the center, but it's not rotating like this. It does all the points when you rotate the circle are moving at the same speed.
It's it's a one-dimensional situation.
Yes. When you go up to the four-dimensional sphere, then you have the same thing. They're rotating around the center of all points are moving at the same speed, and there is no pole. They're rotating around the zero in the center.
Is it a cloud?
No, I'm just talking... No. They're rigid. It's rigid. It's
okay.
like every point is attached to everything else,
okay.
and all of them are just moving in such a weird way. It's really weird. And if I was able to show you, I could show you how it would work like that. It's freakish, but for some reason, these points, even though they're moving around, the distance between them stay fixed, and they're all moving at the same speed. There's no pole. And the same is also true for the eight-dimensional sphere. And this is connected to the division algebras. And those are the only ones that this is possible to do this for. And I'm saying there has to be something here. This is too freakish to be a coincidence.
What about Wolfram, when Wolfram says that math is just describing the crystallized bits and there's all the fuzzy bits that math doesn't describe too?
That's very interesting. But what I'm saying here is that if Wolfram was running some sort of natural selection kind of cellular automaton, then what kind of structure is stable long term? It has to be some kind of conservative mathematical structure. So if it's somehow important not to have a pole, to have a singularity in your sphere, if you want every point on the sphere to be the same,
then you can't have poles.
Then you can't have poles. So when you rotate in a four-dimensional sphere, you can't tell which point you're standing on. Every point is unique. Whereas if you're standing on the Earth, you can tell that whether you're standing on the equator or on the North Pole or somewhere between. You can tell your latitude. But you can't do that on the four-dimensional sphere. So it's more symmetrical. Every point in this space looks the same. Almost like if they have the same laws of physics. Right?
Right.
So it's not like in some regions of that sphere, they have different rotation behavior. All of them behave the same all across. So now, why is it such an attractive idea to have the universe be a sphere? Well, we're living on a globe, right?
Who says the universe is a sphere?
I am saying that it's a very attractive idea, and I think that it is a sphere. And here's my idea for it. If you're moving in the olden days, they believed that there was an edge of the world. You moved on the flat world, and then you just fell off, right? But now we know that no, we're actually living on a closed system where you can go in any direction and you get back to where you started. So there's no edge.
Well, I thought they hypothesized that you could travel straight in a straight line and come back to where you were, and they found that wasn't the case. They found that
now today we can do that. Now we know that if you're going only east, or if you move west, you end up back to exactly where you started.
But in the universe, they had that hypothesis that.
Oh yeah, no, but that's my thing.
That it's shaped
I believe
like
that
a
this
saddle.
is true.
You think
I believe that this is true.
But they measured it and found it wasn't the case.
No. what they measured is that they couldn't find any curvature to space.
Yeah.
But that's not the same thing.
Well, how? So you're okay. Go ahead.
Now, so one of the things that I'm going to publish a paper on this. What I found is that the Octonian, the 8-dimensional sphere, you can make a subspace of that, like almost like an equator. Like think about it like this: on your 2-dimensional sphere, the one we're living in now, on the globe, the equator is it doesn't have curvature.
It's a straight line.
It's like if you cut it into the circle and lay it on a piece of paper, it's not going to be bumpy. Like if you try to cut the 2-dimension the Earth and put it on a flat map, you can't do that. You have to make a projection out of it. But if you just take the equator and put it on a map, you can do that, right? So that is flat.
Any given line.
Any equator line, any kind of like great circle,
Right.
is but like it can't be just like it's not enough to have a circle near the pole, like a latitude at 89 degrees. That's not going to be flat. You can think of yourself holding in the North Pole and you're moving in circles around the North Pole. You actually have to. It's not like that. Okay. Anyways, so what I'm saying is that what I have been able to do using the Octonians, I have been able to create a certain set of like multiplication of formula where I get a flat 3-dimensional space on the 8-dimensional sphere, and it's flat, but it goes in circles.
Oh, so that's why you okay. Now, if we do that, then I'm just gonna find that everything's connected, entangled, one dimension. The law of unity. I mean, we're all on one sphere.
That's true,
or something.
but this brings you no longer than Deepak Chopra.
Well, where did it take you then? I thought that's all it was taking us to.
No, but the thing is, like, yes, we are living in one universe, but like that's not physics. That's just like that's metaphysics, right?
Yeah,
so
which is no. It's interesting that physics mirrors metaphysics so well, though, in that way.
No, it obviously has to, right?
Well, it shocked the scientists.
Maybe it did, yeah. Maybe it did.
They were shocked to find entanglement across the entire universe, all particles entangled through a field.
But Newton wasn't shocked, right?
He believed in it.
Galileo Galilei said that God has written how did he say that the language of the universe is mathematics. It's God's language. That's what Galileo Galilei said. So he was sort of like he was taking it for granted that if we started doing science on the universe, we're going to find mathematical relations that reflect metaphysics. And Newton also believed that. He rejected all this metaphysical speculation crap that we saw from the rationalists. So he's one. He had a specific name for that. He called it hypothesis. We now have a different meaning for that. But he said, I reject all hypotheses.
Yeah.
And by hypothesis, he means a metaphysical speculation.
Yeah, just conjecture out of nowhere. He said you've got to...
Without any foundation in facts.
And nowadays, I think it's a bad thing to use that word the way we do because people think you just pull a hypothesis out of nowhere and then you go test it. And that's not true. Hypotheses come from previous facts and observations.
That's right. Now, so when I'm doing all of this thing, I understand that this is much of what I'm talking about here is far out into the land of metaphysical speculation. But I do have mathematical things that are not random. I have facts from mathematics, and I know that they're connected to physics. But it's just so barely connected that it's like having the most difficult Sudoku puzzle ever. You just have a few clues, right? And most of it is unknown. So I don't expect to solve the riddle of the universe But I think that what I'm doing is valid as long as I'm fully aware that I have to do lots of speculative search to weed out possibilities. And as long as I don't fall into the trap of getting in love with my own speculations and saying this is how the universe really is, then it's okay. It's an acceptable and valid approach for a physicist to do that. But what we're seeing now in physics is that much of modern physics is precisely to just build on top of mathematical fantasies.
Even totally arbitrary mathematical fantasies.
Well, there's some sense that you can see why they would want to pursue that. Some of this makes sense, but it has such huge speculative content.
Why string theory? It just the vibration of some individual little thing leads to everything. Why? So do you?
They're trying. The whole spiel of string theory is that they're trying to solve the problem of combining general relativity with quantum mechanics, and they can't do it at the moment.
Well,
they know
it's been going on
for a fact.
It's been going on for more than 40 years, right?
No, for longer than that.
Yeah,
almost 100 years.
Wow.
And what they have known for about 100 years that these two physics theories are both highly descriptive of reality, but they're also mathematically incompatible. They cannot be merged. Well, and I can explain why very simply.
Why?
General relativity assumes that at the basic fundamental level of reality, the world is smooth, like smooth surface. But quantum mechanics says, no, it's not smooth, it's quantized.
Granular?
It's granular. It doesn't have smoothness. So the lower level you come at from in physics, the less smooth it becomes.
Now, is it might possibly going to be the case that these just describe different levels and they're not going to be compatible?
Wolfram thinks that no. He says that space-time is an emergent phenomenon, that gravity also is an emergent phenomenon, that you can unify them, but that the behavior that we call general relativity emerges from these tiny interactions at a local level.
Yeah.
In that sense, you can say that it lives on it exists on an emergent level, but you can reduce them both to the same kind of local interactions. That's his theory, and he has been done a lot of really good work on that with his cellular automaton.
Now, to make a parallel, I would say that the study of alligators doesn't make sense before alligators evolved. And the study of the system we have today only makes sense in the sense that it has come to be. It's emergent.
I agree. And so a lot of the work in physics now is working down the wrong road, I think, because it's speculative.
So
it's too speculative.
We're studying the system we're in today, and they're trying to speculate on things that might not be available to us.
Yes, such as, for instance, both string theory and supersymmetry, highly related subjects, they often end up with like, oh, this is true, but we have to have like a collider, particle collider, the size of a galaxy to test it, right?
Brilliant.
And then they also have the many world hypothesis. They say that, oh, this universe we're living in is completely improbable. It's basically zero probability that we live in our universe by chance. But we solve that by saying we're pretending that there's like a gazillion possible universes out there, and we happen to living in the one that's habitable, and that this is the anthropic principle. We are here to observe that we are alive. Now that's true. I mean, the anthropic principle is true, but it's just like a cop-out. It's a very cheap solution because it's not testable.
Well, it's a statement that no test is possible, that we just have to accept the fact.
That might be the outcome. But as a scientific theory, to say that there exists infinitely many universes or infinitely many corners of the universe, and we just happen to be in the habitable one, that's a cop-out.
And that's what they're doing with their...
Because we should be able to observe something that indicates it. We have to have experimental basis for that, and we don't.
Well, we've this has just been fun physics chit chat.
Yeah.
Usually we accomplish something, or at least try to anyway, or try to ruffle some feathers. We probably ruffled feathers, huh?
I hope so. We have to have a controversy.
I'll have to make
now,
sure.
This is only interesting for people who are interested in this sort of stuff, and that's not most people.
Yeah. I'll have to make sure Existence University gets this. He's the one that's so mad at me about my displeasure with dark matter.
You have a displeasure with dark matter, and he is very angry at you about that.
Oh yeah, yes, very upset about.
Can you explain that so now we can title something with Existence Universe in the title?
Oh man, well, we didn't discuss dark matter enough. But
I actually did address it. It's just spray painting the universe with free variables.
Oh, that's right.
It's a cop-out.
The cop-out of dark matter.
Yeah.
Well,
it's just like saying I don't have a good solution, so I'm just going to have a bad one.
Right. Now, the description, there was this one video that he sent me where a guy explained dark matter, and at one point he says, it could be anything. As a physicist, I spend all my time wondering what it is, and then he goes through and he names like 25 theories that people are currently working on, and he says, this is fun, I just sit around all day and try to figure out what it is. And, you know, he's making fun of his field right there on the stage, looking like an ass.
And here's a really ironic part. Most likely, all those 25 things that they're studying is probably wrong.
Oh,
all of them.
All of them, yeah. They're all based on bizarre faults. Well, they're all theories of what is dark matter. What is this 95% of the mass of the galaxy in the ring around the outside the galaxy? What is it? Wrong.
Yep.
Now, what do you think it is? Do you have any ideas on it?
I am very into the electric universe theory of it. I'm very interested in that. Now, there's some woo-woo in there, but a lot of it is solid. I know, like, I have a connection with real physicists who take it seriously.
Oh, yeah?
Like Eugene Bakashov, I think he's Belarusian physicist, and he's very interested in this. So basically, here's the idea: if electricity plays a far greater role in space, that solves a lot of problems.
Yeah, a lot.
Because if electricity is such it's like a 10 to the, how much is it? 10 to the 40 times stronger force
than gravity.
Than gravity. Yeah. It's like you just need one electron, and that electron is stronger than the whole gravity of the whole Earth at a certain distance. It's crazy.
Yeah, it can attract a sock that needs an electron can pull one up from the Earth. The Earth can't hold it.
That's right. So that's how strong electricity is. So you don't need a lot of it. So it can be almost no electricity in space, and still it just completely swamps gravity.
And that's why we could find the filaments, that the galaxies are all arranged on these filaments.
Yeah, notice if you take it, just Google. You can even do it now, just for the audience. Google the dark matter universe, dark matter, and look at the images that pop up.
Dark matter universe.
Dark matter universe. And one of them, if you look at the images, one of those images is going to be like a filamentary, like a purple thing. Do you see that?
A purple thing.
Yeah, well, it's a filament. It looks like filaments in space.
There's certainly, there's one, and then bright spots here and there. And those bright spots look like stars, but they're actually clusters of billions of galaxies.
But if you so some of those, these are like simulations that they've made of dark matter. How does dark matter have to look like in order to explain the structure of the universe?
Yeah.
And those pictures, just by extraordinary coincidence, looks exactly like Birkeland currents.
Yeah.
Filamentary Birkeland currents. So it's like they want so desperately to have some kind of positive and negative, like they want to have a positive and negative attraction kind of thing, repulsion and attraction, but they can't get it from gravity alone. So they have to put in all these fancy dark matter things that emulates electricity, basically.
Yeah, it does the same thing that electricity would do.
Yeah. So that's my theory. So when I saw those filaments in dark matter, I was like, hello, that is just like taken straight out of Birkeland currents and electricity and so forth.
Yeah, and I've seen where they do that. They say there must have been filaments of dark matter, blah, blah, blah. And it's like, well, wait, why do you get... So your dark matter now is just occurring everywhere in every piece of the history of the universe to make everything work. Just so.
This is why I'm saying that they're just spray painting the universe with stuff they need to make their theories work. Yep. So they're emulating another force, electricity, using funny dark matter.
Now, let's just remember what it is they're trying to preserve. It's gravity. They are trying to keep gravity to be the ruling force.
Yes.
Which
they are.
Which, as we've seen, Einstein's gravity is not the final answer. We know that with Newton. Even moving the planets around the solar system, we can't. Gravity is just fuzzy. It's not correct. We have to account.
There are issues with Einstein's relativities, and it doesn't, and we know that it doesn't integrate well with quantum mechanics. So let me just give you if you're not blown away by this, you're not blown away by anything. This is called the greatest remaining mystery in physics, and it's just like also called the greatest embarrassment in physics, because according to general relativity, if there's energy in space, then you have curvature of space. So based on our observed curvature of space, we can find out what the background quantum energy is, the vacuum energy, how much energy is in vacuum, right? But you can also calculate the same number from quantum mechanics, and the number you get from quantum mechanics is 10 to the 120 times higher. So it's like a 1 with 120 zeros behind it, times greater than the result you get from general relativity.
Wow.
So it's like, that's not just a little bit wrong, but you're not just in the wrong universe, you're just like in the wrong neighborhood of universes.
So you're saying relativity takes no account of, or takes almost no account of the background energy that the universe is made of or exists on?
Well, what I think is that the way they do the calculation, we don't understand it yet. The vacuum energy, the way I understand it, is connected. They call it virtual particles.
Yeah.
And what they mean by that is that this is something that you can describe as particles, but it's only like a soup of behavior that is connected to real energy.
Well, can I just mention, if I make sure I'm following you, a virtual particle can pop into existence and then fade out of existence as long as it doesn't interact with any other particle. Then it doesn't.
It can interact, but it has to add up in sum to something good and real.
Well, I was going to say it can't interact with other particles, and that because that would violate the law of conservation of energy and the law of identity.
It can, so long as the law of conservation of energy is conserved. So it can do anything it wants, so long as the law of conservation is conserved. Right?
So if a virtual particle pops into existence and interacts, then what? Some other particle somewhere has to pop out of existence in order to.
Well, I don't know the details. Maybe you're right about that. I'm not going to make a final statement about that. I'm just going to say that this is considered like a virtual behavior of quantum fields. But I think that the error in general relativity is that they treat the virtual particles, virtual energy, as real energy, causing real curvature. I think that's wrong.
It's just
so the energy. So the energy might be there, but you just can't. It doesn't contribute to this so-called curvature of space.
Okay, it's only it only becomes part of space if it actually becomes real.
Real, yeah, and only then does it have a gravitational effect.
And so they're measuring the potential, the background, or they measuring?
No. What they do is that they use quantum mechanics to calculate the background energy level.
Okay.
So it's a calculated figure, and what they get is that the normal number they get is infinite, but then they say infinite is a little bit too high. So then they say, okay, it's unreasonable to assume that below the level of the Planck length, which is 10 to the minus 34 meters or something like that. I don't remember it, but you can't have wavelengths lower than this Planck length.
Right.
And if you say that that's the cutoff level, like you can have energy with waves all the way down to there, but not long further, then you get this absurdly high number.
Huh. That's
10 to the 100 plus something, or like it's just an insanely high number.
Huh. All right. Well, what do we do with that? We say that they're just lost in math?
Yes, that's the short answer. That we don't know what's going on, and it's an embarrassment because it just shows that something is not wrong. It's terribly wrong.
With what? Quantum mechanics?
Physics. With physics, and we don't know what it is. We don't know if it's quantum mechanics. We don't know if it's general relativity or both.
Well, quantum mechanics is just statistics right now.
Yes, statistics with a lot of nice math on top of it. So it's very close to the epicycle thing.
Yeah.
I mean, it's crazy. They were actually able to navigate across the oceans using epicycles, right?
The math from Ptolemy's systems, yeah. It was
and
very,
they
very
refined
accurate.
it over hundreds of years, and they were able to get a refinement that was so good that they were able to navigate with extreme precision. And it took 100 years of observation to refine the Copernican model, with the heliocentric model, to make observations so that they got equal amount of precision. So for 100 years, they were still using the epicycles because it was more accurate in practice.
The utterly false epicycles.
No, but here's the thing: in the mathematical sense, it is not false.
Right.
And here's an example of this. What the epicycle thing is really doing is it's doing what's called a Fourier transformation.
Shall I Google Fourier transformation?
I can do better for you. I can find a really cool video that you can share. Okay, let's see. Yeah, this is cool. I'll share this with you now in the
Yeah, there's a lot of videos on.
Yeah, but like I'll share one specific with you, which is just amazing. There you go. You can have that playing in the background, and everyone will immediately understand. This is epicycles. This is they're using a frequency analysis. They're breaking down patterns into waves. Fourier analysis can be used to do a spectral analysis of sound. So you can break down sound into these epicycles. So,
sorry, I got the sound.
Oh, you can just turn on the sound. So people can watch in the background that they're building up. I haven't seen the beginning, but you can even go forward towards where things are happening, because he might be explaining something in the beginning there. But you will start seeing when he's starting to build up the, or maybe he has it. Let me see. Yeah, no, that's it. That's it. That's epicycles. He's using epicycles here to draw any kind of shape. In this case, he's doing it to a note. And he has all sorts of shapes that he uses these epicycles for. And some of them are really crazy.
And these are just circles moving around circles.
Yep. That's epicycles for you. And what you're seeing there is what is called the Fourier transform. He has done a Fourier transform where he's doing an analysis of these circles going in circles and using complex numbers, by the way. This is precisely complex numbers. And then he's using this just to try to map out a certain path in X and Y. And then now this one contains something like 100 circles. So he needs something along this 100 frequencies to build this model. So these are just roughly 100, I don't remember exactly, but like 100 circles moving at different speeds and at different radiuses.
Mm-hmm. So what are we saying with this? This is
mathematically correct. This is just a method for describing the world using circles. That's all that is, and that's what the epicycles did with the planetary motions.
Right. Ptolemy was wrong that Venus was going around the Earth, but he was right that Venus was going to come up at 7 a.m. on June the 8th.
Yep. So the epicycle model, you can use it for anything. You can use it to predict to replicate the sunspot cycle. You can any kind of pattern you can replicate using these epicycles.
And in the same way, quantum mechanics is right that such and such is going to decay or do this or that, but it's wrong about the why it's happening or what is happening.
Here's the thing. We don't know exactly why it's wrong. So most of it may be right, but we don't know exactly which part of it is right and wrong.
And so you say most of it may be right. I mean, how much of Ptolemy was right?
Yeah, that's what I'm saying. In his case, he was completely wrong. But in a very interesting and in an interesting and non-trivial way that he was wrong. He was right that here's what he was right about. Things move around a body. Right? But he got the wrong body.
Yeah.
He said it was the Earth, but it was actually the sun, and it wasn't circles, so he was wrong about that too. It was actually ellipses.
Right. Yeah, wow, he couldn't... Yeah, even Copernicus didn't get the ellipse thing, though. That was left for Galileo and Newton to work out. Or Kepler.
It was for Kepler. It was Kepler who got it right.
Yeah, and then Kepler didn't understand why.
No, but he made the Kepler's laws from it, which was great work. And now he's... I don't know how far you've gotten into the video, but now he's making like Britain.
Yeah, we saw the Britain part.
Yeah.
Now he's doing the next bit.
And he's saving the best for last, so he's now just zooming in, so it's not showing the whole thing. So he's just showing what you can do with epicycles. Now, I want to stress that what you can do with epicycles like this just shows you the power of math. That you can do this is really spectral analysis. That's what this is. So when you're seeing someone doing like taking a spectral analysis of sound, saying there's a lot of bass here, there's a lot of this kind of thing, then that's exactly what they're doing. They're creating, they're using sound, circles to describe sound. And since sound is a wave phenomenon, it's very suitable. And in that particular case, when you have a wave phenomenon, then we say that in that particular case, it's not just an epicycle theory. It's not just it's not just an application. When you're dealing with actual wave phenomena, then it captures something that's real. So when we say that the spectral analysis picks up on waves, on bass sound, we can hear it with our ears, that there's a one-to-one correlation between the frequency and how the pitch, right? How we hear it. So we can hear that this theory of frequency of sound is correct. We can see it and hear it. But in this case, this is just something that's happened to be correct. There's no intrinsic waves to these patterns that he's drawing here. It just happens to be using a mathematical technique to map out reality. And this may be, I say may, this may be what's going on with quantum mechanics. That quantum mechanics is just an epicycle theory. That's very accurate, but it has no fundamentals to it.
Yeah.
Or it may have fundamentals to it, but just like with the Ptolemaic model, they may get the thing wrong. It's like something is spinning, but it's the wrong thing that's spinning, and it's not circles or like this, but it's something that looks like circles.
Right. Yeah, that's what I think, and it may be the case that when they do discover whatever it is, a lot of our current statistical knowledge will be preserved, in the sense that they knew Venus was going to be coming up on June 8th. Even after they discovered that the sun was actually at the center, they still knew that June 8th was the day Venus was coming up at 7 a.m. So
that's right.
We might find out what the real background explanation is, and yet a lot of this information will remain true. You know, it's been said that quantum mechanics is so accurate you can predict the width of the United States within down to the width of a hair or something like that. It's really, really accurate. And
I'm not very impressed by that. And the reason I'm not impressed by that is that I can do that without quantum mechanics too. And I can explain now here. Suppose that I tell you, I'm going to give you an instruction now. If you take an airplane, and it doesn't matter which airplane you take, to Australia, you go to Sydney, and I'm going to give you a specific address in Sydney. And when you get to that address, there's going to be a rock on the left side where you can get a key, and you'll open the garage, and I can describe the garage to you so that you know that are in the right place. When you get in the garage, there is an electron microscope in the left corner of the room. And I want you to go there using into the left corner, and I want you to find inside of a little petri dish, I want you to find one atom for me using the electron. And I've limited, and I'm going to tell you which region of the petri dish this atom is, so you can search for it. Now, I just, with words, simple words, given you a way to find something that's a map that's far more accurate than the width of a hair, not just from here to America, from within America, but to the other side of the globe, Sydney.
Okay.
Right?
Yeah, without using quantum mechanics. All right.
And I just gave you a map for that. And so finding something that's very accurate in this way, this is the same type of accuracy that's behind this Ptolemaic circle that we're seeing now. The the epicycles. It's just you list make a long list of how do you get there, and that's what we're seeing right here, and that's what I just described to you for finding a place in a very limited place in Australia. And so I'm not so impressed by the fact that quantum mechanics is accurate. And once you get over that accuracy, shock of its accuracy, then you are more open to the fact that it can be accurate even though it's completely wrong.
Yeah,
right?
well, yeah. I mean, in a certain sense, it has to be accurate in the sense that they test it and retest it and retest it, but they just don't know what they're retesting, and they don't know they have no conception of what they're actually gaining knowledge about. So they're not really gaining very good, solid knowledge in a certain sense.
That's right. And sometimes in the future, we might have that knowledge. But at the moment, like if you ask someone what is the meaning of quantum mechanics, what is it? What is it describing? No one has an answer for that. Like I have my speculations about it, but it is speculation because we just have equations that happen to work.
That happen to work.
Yeah.
We've taken things in reality that occur and making equations for them.
Yes, and we don't know why. Now, Newton did the same thing to some degree. He said he doesn't understand what gravity is. He never made a claim that he can understand exactly why the gravity follows the inverse square law.
Yeah.
But what he was able to identify is how it works. Like it's the phenomenology of it, right?
Yeah.
So
yeah.
It is an accurate description to say that there's an inverse square law. And it's an accurate thing to say that the most central body in our solar system is the sun. Right?
True.
So he did get all of those things right, but he is absolutely right also that he didn't actually understand gravity, and he made no pretense to understanding what gravity really is in a metaphysical sense.
But in a metaphysical sense, we can say that mass attracts matter, and it seems like we can be done with that and walk away.
Yes, but if you want to find out what's going on under the hood, that there's something deeper going on there, then he wasn't able to answer that.
Why does mass attract matter?
Yeah. Now, and notice that this is a rabbit hole. There's always another question you haven't answered.
Yeah. Like I say, are you sure we can't just say mass attracts matter and walk away? Why does mass attract matter? Gravity.
You can say that, but you're going to get Existence University banging you in the head.
Yeah. He's going to want to know why. Because we got electromagnetism, we can talk something about why that attraction occurs, but we can't talk about gravity. It bends space, but space doesn't exist, so now we're stuck again.
Yeah, I'm very unhappy with that language. I understand that I have to comply with that when I'm speaking with physicists, but this yoga lessons of space, I don't like it. I don't think that's the correct way to conceptualize. I have my own ideas, but they're too immature at the moment to say that I have a theory.
Do you think we have to have the ether?
Yes.
Yeah, I think we're stuck with an ether. I can't find a way out of it.
But it's going to be a relativistic ether. It's not going to behave as nicely as the ether of the 19th century.
Right. So
one of the strange things about the ether is that we're always standing still with respect to it. Everything in the universe stands still with respect to the ether, even though they're moving with respect to each other.
Is the ether just the Higgs field?
No, there are things in the universe that can behave just like I said. So, for instance, consider the following. If you look at the moon, which is approximately infinitely far away, right? And then you start moving around, then the moon doesn't move. It doesn't it just stays where it is. So from your perspective, the moon, no matter how fast you're going or anyone else is going, the moon is standing still. So one possible solution is that the ether is sort of somehow infinitely far away, like the stars.
But it's everywhere. It's local. There's no distance.
So there has to be some, like, in order for that to make sense, infinitely is virtually infinitely. Like we're tiny creatures, and we're seeing some sort of a reflection of something that, from our point of view, is infinitely far away. That's one possibility. There's another way you can get something to stand still, even if everything is moving with respect to it. And that is if you're standing on a sphere and you're looking at the center of the sphere, the middle of the sphere is standing still. No matter how fast you're moving, you're going to see that the middle of the sphere is standing still with respect to you. And this is true for everyone on the sphere. No matter how fast they're running, the center of the sphere looks like it's standing still. So that's sort of like wrapping the infinite thing on the inside. It's like taking a glove and turning inside out. So now that you're putting this thing in the center of the sphere instead of like on the outside. Those are neat mathematical tricks. I'm not making any claim that this is how the universe is. Those are just two real-world examples of something where we can move with respect to it, and everyone sees that it's standing still. So the stars are standing still with respect to us because they're so far away. And if we're standing on a globe, a transparent globe, and looking into the center, everyone is going to see the middle of the sphere standing still with respect to them. Those are real world examples. So I'm just noting that in both of those cases, you have something that you could say, I can see where that can fit into a physics model. Like this standing on a sphere thing, that would be nice if the world is a sphere, and if we're moving in one direction far enough, we're getting back to where we started, that kind of thing. So there's a lot of niceties here that allow. It sounds extremely weird that the ether should be standing still with respect to us, but it's not physically impossible. It's not an absurdity, because there are things in our world that behaves like that.
Even if we go up close to the speed of light, wherever we stand, as we're standing in our spaceship or whatever, the ether around us is holding still.
Yeah, and that's true also for the stars. No matter how fast we go, we see the stars standing still because they're virtually infinitely far away, even if we're traveling at the speed of light.
And do you think the ether is? Do you think the ether's granular, or is the ether a jam?
I think that the ether is some kind of like a fluid of some kind, but it could be granular, like a pile of sand.
Well, it's either fluid or it's granular.
No, it can be both at the same time.
A fluid's like made of atoms, which are granular.
Well, like a pile of sand can behave like a fluid.
But it is granular.
Yes, but granularity also means that it doesn't have to behave like a fluid.
So what do you think that the ether could be granular but behave like a fluid?
Yes, like on the macro scale, it behaves like a fluid, but locally it's granular.
Why do we now? What if it's not granular? That would mean that the entire universe is one.
Yeah, but now we are back into Deepak Chopra territory.
But
right.
if that's just if the whole universe is written on the surface of a single dimensional item, then we don't have to be Deepak Chopra about it. We can just be law of identity about it.
Yeah, the problem is that it's just speculation.
Yeah.
Everything I've said now is speculation, but but I have certain reasons for believing that the ether, like from physics, that the ether is some kind of fluid, and that it behaves like this. Let's put it this way: quantum field theory is an ether theory. It's a relativistic ether. It has all the properties of ether, quantum fields, but with the one additional little thing, that the ether is standing still with respect to us always, no matter how we move. That's the only thing that's different.
They had to add that in, you mean?
Well, that comes from special relativity. So when Einstein, not the general relativity, but when he first made sense of that the speed of light is constant, that was special relativity. The speed of light is constant if you're standing still with respect to some kind of fluid. So for instance, air, if the air is standing still with respect to us, then the speed of sound is always going to be the same.
Right.
But if we are moving like in a car and we are then measuring the speed of sound, it's going to be either faster or slower, depending on if we're moving away from it.
See, that's why I have to mention some background dimension that everything's written on that is not this distance between things is not true. That's an illusion of our way of living in this area of the universe. There's actually no distance between things. Distance only says that these things take time before they can interact. But there actually isn't a distance between everything in the universe in the sense of whatever it is, the Higgs boson wave or the field or identity as such or the ether. It seems that there is no distance.
I can grant you that this is a possible outcome. In other words, this may actually turn out to be true, but the way you said it makes it sound like this is now a definite statement, but it's pure speculation, just like everything I've said now so far. Well, like the thing about ether, that's not speculation. Quantum field theory is an ether theory. They don't call it ether, they call it a field, but it's an ether. It's basically the ether theory, because it's so I'm on solid ground, metaphorically speaking, when I say that the ether exists, because the quantum field theory describes an ether. But from there to draw a conclusion that it's granular, that's pure speculation. That it's a fluid, that's also speculation, although there's some indication that that may be true. And it's certainly speculation that there's no distance between things. That may be true. We might be sitting in a matrix-like world, but it's speculative.
Well, distance is just our description of events over time.
Possibly, but you have to actually get somewhere. It's true that you can all distances can be measured in time, so to speak.
Yeah.
But it's not only measured in time.
There's events over time. So there have to be things there are events that occur.
And those have properties, and those properties extend in space, right? And they color your measurements. So you can't get away with the fact that you do need to have 3 dimensions in order to describe the world around you. And you can say that, that's just us. But we are the only thing we have.
But it seems like you can't get away from the fact that the 3 dimensions
are connected somehow to a oneness.
Yeah.
Now, we do live in one universe. Even though this multiverse theory is popular at the moment, we can't get away from the fact that our universe is one.
Well, I'm very displeased with these people. Uni means one.
Yeah.
The Greeks covered this. If you find something in a little pocket next door with a little telephone line going to it and you call that another universe, the Greeks covered it. That's part of our universe too. We've already got that.
Agreed.
If we
but
wanted
what they mean by multiverse is that they are not connected.
Well, then if they're not connected, we can never know anything about it. There's no telephone line going over there for us to talk to them and figure out what's going on, so it's just fantasy. Yeah. They're just making shit up now.
That's what I'm saying. Then when they are saying that the reason we are living in a fine-tuned universe, it's because we have all these separated universes, and we are naturally selected from that cluster of infinitely many universes. That's just speculation, and it's pure fantasy. It doesn't have any bearing on reality. It's a cop-out, as I said. It's a way to say that I'm not going to tackle this problem in the mature manner. I'm just going to wave my hands.
And make something up. Totally make something up.
Yes, make up something that does so I can feel good about myself, not looking for an answer.
It reminds me of the Russian physicist who came up with the idea of a quantum foam, and each bubble was a universe. Yeah. And then he works on that feverishly mathematically for years. Never going to get anywhere with it. It's just a fantasy. It's just as good as The Hobbit. Not even as good as The Hobbit, because at least we can read The Hobbit and get some sort of moral message from it. So it's not even as good as The Hobbit.
That's true. So I'm very skeptical of that kind of science, in scare quotes. I don't like that at all.
Yeah.
So some form of speculation, like the one we've been talking a little bit now today, you have to do that if you are working in the field of physics, just as part of exploratory work. It's part of creativity. But eventually, if you don't connect it to reality, you have nothing.
Well, you have to have hypotheses, and you have to take account of evidence that comes your way.
Yeah.
I didn't know what exactly they were going to find with their particle collider, but when they found the Higgs field that entangles all particles, it didn't take me very long to wrap my head around that and say, well, of course all particles are entangled. The universe is one, and everything has identity. So,
and that is true. Like at a deeper level, everything must be connected to each other into like a one universe. Otherwise, it wouldn't be a universe.
Yeah, and that's what they found. So
now, what I did. This actually does connect to the dim, and like in a strange way, I think I mentioned this Sufi mystic. I didn't know he was a Sufi mystic at the time. That I discussed lots of these crazy ideas from physics with 20 years ago when I was much younger. And he had a crazy idea, which later I saw had a lot of overlap with dim hypothesis. He called it, his theory was that we're living between systems and metasystems. And a system is what he calls complete order. 100% order, everything is fused into a complete oneness, and a metasystem is complete disorder, completely disintegrated, disassembled system. So he would then think of this as, if we translate to dim, he says that the metasystem is disintegration and system is misintegration, like
total integration, yeah.
Total integration, yeah. And in between there's a special kinds of system that are partially integrated and partially not connected.
And in there, do we find physics and free will?
Yeah, and you find reality there basically. So, and here's the interesting part: he defined. I remembered this for all these years because I thought it was a very nice way of looking at it. He says that this. There is one layer of organization between system and metasystem, between order and absolute integration, that is, he calls the social, the level of the social. And he says it can be, you can use the plus sign or the conjunction, like and plus or a conjunction, as a metaphor to describe this. Because he says, at this particular stage of organization, the plus sign or the and sign is just enough to keep them together, but that same thing that keeps them together, joins them, is also the very same thing that keeps them apart. So they're not fully integrated, but not fully separated. And the thing that is keeping them apart is also this thing that's binding them together.
Is that marriage? Let's say is that like marriage, so that you couldn't really add them together. All you can do is bind them together.
Yes. Now, marriage is one example of that, and he uses that as one example, where you become a unity where you're not fully a unity, but you are bound together. And he says this about social relationships in general. Like, we are social creatures. What does that mean? It means that genetically we're bound to other social beings. Like, it's in our genes that we live around other people. So we're held together with other social beings. But at the same time, we're not fused together. We're not the same thing that holds us together, language, blah, 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 all, rational thought, all of these things. The very same thing that holds us together is also the same thing that holds us apart and keeps us individual. I found that a very fascinating idea, and it had a ring of truth to it.
Which echoes the fact that people can come up with true ideas, true conceptions, true understandings of reality, as long as those echo reality, they're true. They don't have to have, like, he wasn't an objectivist.
No.
He was a mystic of some kind. But
he was a mystic, but he had these visions of something that struck a chord with reality every now and then.
Yeah.
Now, the best way to describe his idea of the conjunction as being that which keeps it together is the same thing that keeps it apart, is one in the many, right? Mm-hmm. That's a state where you're holding together all the many without fusing them, but you're holding them sufficiently together so that you see a one in the many.
Yeah, realize that
if you fuse them too hard,
you're an individual human, but you're also a human.
Yes, right. And he says then, if you're fusing them too much together, you get just one without the many. That is what he calls order, where each component now has no individual reality. One without the many, then that is what we call a system. And a system consists of a whole built from parts. And a part has no existence other than being a part of a whole. So parts, like a cogwheel, is defined entirely by its function in the whole. That's a system. There's no individuation there. Right. There's a distinction, but not sufficient to make that cogwheel a real thing in itself. It's a cogwheel, like it's a blob, in that sense it's real, but as a cogwheel, it only exists as a functionally entity, a part in the whole.
As opposed to, say, an atom inside of a cloud of Brownian motion. Brownian motion being the other. Like that the cog has a set around it. The atom in a Brownian cloud, a cloud of Brownian motion, is.
I'm reluctant to make the jump to physics here because we don't know if atoms are actually alive or if there's what kind of entities they are. So a cogwheel is a human-made thing. We've molded it into a special form, and that thing in itself has no existence outside our desire to make it work in that whole. And that's what he means. When you take these entities and you fuse them into a whole, into order, individuation disappears.
Talking politics now.
That's one way that he didn't only talk about politics. He talked about lots of stuff. But like if you're taking individuals and you're turning them into cogwheels in an organic whole, like Hitler did, and the Nazis, that's an example of misintegration, turning individuals into a system where you get one without the many. Or for that matter, in communism, you have the same thing there.
Not that all systems are illegitimate for people to take part in.
No, but he's using it in like systems theory definition.
Systems. Maybe we could say that. Maybe we can make the leap that systems that destroy the individuation of the units inside of it are inappropriate or metaphysically maladaptive, something like that. Then we could find some echo of the instance of identity in politics and why you can't negate individual identity with political theories. Well, shall we draw a line and wrap up?
It's 2 hours, so I think this is good.
Physics chat. What is this? Metaphysics 101. Let's see. We had a title earlier. Metaphysics 101.
What about crystal math?
Crystal math 101.
Yeah.
All right.